Hello, this is Mr. Best. Welcome to section 2.6, Rational Functions and Asymptotes. Our focus today is going to be finding the domain of rational functions and also finding the horizontal and vertical asymptotes of rational functions. We're first going to start with the parent function of a rational function, and what a rational function is the quotient of two polynomials. So f of x, we're going to write this as f of x equals n of x divided by d of x, and d of x cannot equal 0 because your denominator cannot equal 0. So the parent function is just 1 over the x value. The domain of this, you can have all real numbers. You can plug in whatever you want into the function, except you cannot divide by 0. So therefore, x cannot equal 0. So your domain is all real numbers except for 0. So we're going to write this in interval notation. Alright, so we have parentheses on the 0 because 0 is not included. And then we'll talk about the range in just a minute. Let's go ahead and graph the parent function just like we did the other day. There's only two nice values you can plug in. When x is 1, y is 1. And when x is negative 1, y is negative 1. And then we just start plugging in some other numbers. When x is 2, y is 1/2. When x is 3, it's 1/3, 1/4. And as x is 10, it's 1/10. And so on and so forth. And if you plug in x is 1/2, 1 divided by 1/2 is 2, 1 divided by 1/3 is 3, 1 divided by 1/4 is 4, and so on. And you can do the same thing on the negative side. 1 divided by negative 2 is negative 1/2. 1 divided by negative 3 is negative 1/3. And then if you divide by a fraction, you get 1 divided by negative 1/2 is negative 2. 1 divided by negative 1/3 is negative 3. So you got a lot of small numbers here, but as these values go on, they get close to the x-axis, but they never touch it. So what we have is a horizontal asymptote. Also, it gets close to the y-axis, but it never touches it. So we have a vertical asymptote. So as the graph, as x gets really close to 0, the y value gets really large. As x gets really large, the y value gets close to 0. And then we have the same thing happen on the other side. Try to do a better job here. A little bit harder than I thought, but so that's our parent function of the rational function. And so our range value, range is your y values. All y values are covered, and you can kind of see that as you go along the function, but it doesn't cross the x-axis, so y will never be 0. So the range is all real numbers also, excluding 0. We have no intercepts. It doesn't cross the x-axis or the y-axis of the parent function. And the function is decreasing where? Well, if you look at this function as you go across, I'm going to kind of use a highlighter, I'll delete this, but as you read this left to right, what is happening to the y values? They're decreasing. And then when I pick it up on this side, y is at infinity, and then as it comes down, y is getting smaller and smaller and smaller and smaller, and gets closer and closer to 0. So it's decreasing throughout the entire graph. So we're going to say that it's decreasing from negative infinity to 0. And it's also decreasing from 0 to infinity. And 0, it doesn't even exist, so it can't really be decreasing on that. This is origin symmetry. If you look here in terms of origin symmetry, remember that it takes and rotates the graph 180 degrees from the origin. So think about taking these points and rotating them. Also, remember on origin symmetry, we go from the point AB to the point opposite A, opposite B. So those points we just plotted, 1, 1, becomes negative 1, negative 1. The point negative 2, 1, or sorry, positive 2, 1/2 becomes 1/2, 2, or negative 1/2, negative 2, yeah. And so that is origin symmetry, which means we have an odd function from what we talked about the other day. And our vertical asymptote is at x equals 0. So that's that vertical line that crosses through the origin. And then our horizontal asymptote is at y equals 0. So this is the parent function. We're eventually going to get into the graphing part of this, but I at least wanted to show you the parent function and a lot of the different things that we had talked about with domain and range, origin, symmetry, odd function, and introduce what that vertical and horizontal asymptote looks like. So on the next slide, what is an asymptote if you haven't learned this already? An asymptote is a line the graph approaches but does not touch. Well, this is the definition that you probably learned in Algebra 2. But this idea that the graph does not touch this is not 100% true. Alright? If you're talking about a vertical asymptote, then yes, the graph will not touch a vertical asymptote. That is true. But with a horizontal asymptote, that's not true. You can have a graph where, let's say this is your horizontal asymptote. It can actually go cross the horizontal asymptote and then get close to it from the other side. So I just want to make sure I'm clear that I got the two kind of definitions below it for vertical and horizontal. So even though a lot of times we learn that an asymptote is a line the graph approaches but does not touch, and that's not 100% true. That's true for vertical, but not for horizontal. There's three types of asymptotes that we're going to learn about. We're going to learn about vertical, horizontal, and something called a slant or an oblique asymptote. We're not going to do that one today. Our focus is going to be on the vertical and horizontal only today. So a vertical asymptote, alright, is a line x equals a. X equals a is a vertical line of the graph of f. If f of x approaches infinity, so as your y value approaches infinity, or your y value approaches negative infinity, what is happening to your x value? It is approaching some value of a, either from the right or from the left side. Okay, so as y gets really large or really small, the x value is going to approach this value of a, which is your vertical asymptote. So you would write x equals a as your vertical asymptote. Horizontal asymptote, kind of the same idea, but as x approaches infinity, or x approaches negative infinity, now the y value approaches some value b. Okay, so once again, kind of the same idea. It's just depending on if you're doing vertical, you're looking at as y approaches infinity and negative infinity. If you're doing horizontal, you're asking yourself as x approaches infinity and negative infinity, what value is it getting closer and closer and closer to? Alright, so first we got our rational function here, f of x equals n of x over d of x. Remember, n of x and d of x have no common factor. So this is something we're going to have to talk about, because what happens when it does have a common factor, and that's something we're going to discuss later on. So we have to make sure there's no common factors. So we'll cancel any common factors out that we have, and once that part is true, then we can find our vertical asymptotes occur at the zeros of d of x. Zeros. Remember, the zeros are when y is 0, what is x. So we're just going to set our denominator equal to 0. So what values of x make our denominator equal to 0? And remember, our denominator can't equal to 0. That has something to do with our domain as well. So when our denominator is equal to 0, these create x values that don't exist, which are our vertical asymptotes. Horizontal asymptotes, there's a little bit more to this, and you might remember some of this from Algebra 2. Horizontal asymptotes occur at most once. Okay, so we're not going to have two horizontal asymptotes, and are determined by comparing the degrees of the numerator and denominator. Remember, the degrees are the highest exponents of the polynomial. So there's basically three things that can happen. The degree of the numerator can be less than the degree of the denominator, and if that is true, okay, if the degree is less than, and I'll give you a quick example. So Actually, our parent function is this way. F of x equals 1 over x. The degree on top is 0. The degree on bottom is 1. So if that's true, then we have a horizontal asymptote at y equals 0. If the degree of the numerator is greater than the degree of the denominator, then we have no horizontal asymptote. So we don't have to have a horizontal asymptote with rational functions. So once again, this could be an example of x squared plus 1 over x, where the degree on top is larger than the degree on bottom. And then the third one is when they're equivalent. And if they're equivalent, then what we're going to do is we're going to divide by this a and b. But what is this a and b? The a and b are the leading coefficients of the numerator and denominator. So I'll highlight this to make sure. So the a is the leading coefficient of the numerator, and the b is the leading coefficient of the denominator. And so, if I can go back and do this. Oops. So I'll change this. So it's your A and your B. And so if you divide those leading coefficients, then you have your horizontal asymptote. So really that's what we're going to do today, was we're just going to identify our vertical and horizontal asymptotes. We're also going to talk about the domain and the domain. We know which one of these has to do with the domain. It's your vertical asymptote, because your domain has to do with your denominator and your vertical asymptote has to do with your denominator. So let's take a look. First example, find the domain and then identify any horizontal and vertical asymptotes. So on the first one here, f of x equals 1 over x plus 3. Well, your denominator has to do with your domain. So x plus 3 cannot equal 0. So what value of x makes the denominator equal to 0? Negative 3. So your domain is all real numbers except for negative 3. What that was. So negative infinity to negative 3, and then we're going to do the union. And so that means all real numbers except for negative 3. So that also has to do something with your vertical asymptote, because your vertical asymptote is where the denominator is equal to 0. So we just figured that out. The denominator is equal to 0 at negative 3. So your vertical asymptote is at that restriction of the denominator. So x equals negative 3, we have a vertical asymptote. And then your horizontal asymptote has to do with the degrees. So the degree of your numerator is what? So this is x to what power? 0. So you have a degree of 0 over your degree of the denominator, which has an exponent of 1. So if the degree on top is less than the degree on bottom, then your horizontal asymptote is y equals 0. So once again, going back to this slide, if it's less than, it's y equals 0. And there you go. And so those are the three things I was asking for. So another example on B, g of x is equal to x squared minus 16 over x squared plus 7x plus 12. Once we get into some higher degree polynomials, we want to factor them to make sure we don't have any common factors. So on this one, let's see what we have. We have g of x equals x minus 4 and x plus 4. And then on the bottom, factors of 12 that give you 7 would be x plus 4 and x plus 3. So what we find out right here is that this x plus 4 is going to cancel out. So the simplified version, now this is not exactly the same as the original, but the simplified version looks like this. Okay, the domain Alright, still has to do with all parts of the denominator. Just because it canceled out doesn't mean it's not part of your restriction. So both values here, when we're solving this, have to be part of your domain. So neither of these can equal 0. So that means x plus 4 cannot equal 0, and x plus 3 cannot equal 0. So what values of x are not part of your domain? -4 and -3. So your domain, and if we're going to do this in interval notation, it's going to be a little bit longer because we have 2 breaks. So -infinity to -4. And then we'll pick it back up from -4 to -3. And then from -3 to infinity. Okay. Now, going back here, I just want to make sure that we remember when we find the when we find the vertical and horizontal asymptotes, there are no common factors. So we did simplify this, so we've got to look at the simplified version when we identify the vertical and horizontal. So the vertical asymptote is when your denominator, okay, which in this simplified version is equal to 0. So that would be at x equals -3. So our vertical asymptote is at x equals -3. Okay. And then our horizontal has to do with the degrees. Well, the degree is 1 and 1, so we take the leading coefficients, which also happen to be 1 and 1. So the horizontal asymptote is y equals 1 over 1, which is 1. Okay? So that's how you identify domain, which has a lot to do with your vertical asymptotes, but they're not exactly the same. So you can see our domain here has restrictions at -4 and -3, but only the vertical asymptote is at x equals -3. And that's because we had to cancel out the x plus 4, and when we find the vertical and horizontal asymptotes, we only do it with the simplified version. So there's something about that x plus 4. We're not going to get into that today. Some of you might remember from Algebra 2, but we'll talk about, there's still a restriction there, so something's going on there, and we'll talk about that later though. Alright, on the last slide here, I have 3 examples. I suggest pausing me at this point and go ahead and working through each of these examples and then checking back and seeing how you did. Now on this one, I'm only asking for the vertical and horizontal asymptotes. So the domain you don't have to do, but you're still kind of looking at it anyways. So go ahead and pause me and see what you can do. Alright, on example A here, so we're going to do the vertical first. So the vertical asymptote has to do with the denominator. So what value of x makes the denominator equal to 0? So if you add 7, divide by 2, 7 halves. And so at x equals 7 halves, you have a vertical asymptote. So vertical x is equal to 7 halves. Your horizontal asymptote has to do with your degree. The degree is 1 and 1. Your leading coefficients are 3 and 2. So your horizontal asymptote is at y equals 3 halves. And there you go. Alright, on the next example, we can factor the top. By factoring, we're looking for any common factors, which we don't have, so that's okay. So the vertical asymptote has to do with your denominator. X minus 1 cannot equal 0. So at x equals 1, you have your vertical asymptote. And then the horizontal, once again, has to do with your degree. You have a degree of 2 and a degree of 1. It's larger, so therefore your horizontal asymptote is none. So you won't have 1 on this one. Alright. And then on the third one, you have your denominator is x squared plus 1. Now that can't be factored, and if you try to solve for it, what you're going to get is plus or minus I. Well, we're not dealing with imaginary numbers here, and that doesn't give you any values in the denominator that x is going to make it 0. So there's actually no vertical asymptote on this one. So vertical asymptote, because we have no value of x that makes the denominator 0, which means our domain is all reals. So we're not going to have one. And then our horizontal, the degree on top, you don't have an x, but if it was there, it'd be x to the 0. So you have a degree of 0 over 2, so it's less than. So therefore, the horizontal asymptote is at y equals 0. Alright, that is it for today. Once again, really identifying horizontal and vertical asymptotes. Your homework assignment is right there. And we'll look at the graphing part of it next.